Okay, calculus nerds, we're ready for related rates, example number 4. So let's just see where this takes us. I'm noticing I'm clapping every time I start a new one. I'm not sure what that means, but anyway, sorry for wasting your time. You can always fast forward. But anyway, if you hopefully have read example 4, you will see that it talks about air expanding adiabatically. I have no idea what that word means. That certainly sounds like a scientific term to me. Abdominally, diabolically, I have no idea. But here's the point. There's a mathematical expression here for this particular situation. I don't believe there's any kind of picture we can draw. So I guess my point would be that that little formula that the smart scientists have figured out for this particular scenario would basically be the type of equation that we need. It's an et cetera. It comes from another field of study. So there it is, there's our equation. And you know, if you recall the cone head example we just did, example number 3, and who could forget that? You know, we talked about you try to get this down to as few variables as possible. If you read through this question carefully though, you'll notice there's no real secondary relationship given to us. So basically, we're at the point where we just need to treat this as the product of two variables, and that'll be important. We're going to basically go through here, and this is the pressure, this is the volume, and it mentions in the narrative that that C is a constant, which will be very important as we move forward. So basically, there's our equation. They gave it to us. So, idea number 2, what rate do they wish for us to determine? And so, if you read the question, then let's go back to it again. I understand it might be hard for you to see this on the video, but I'll remind you, you have the printouts or the PDFs that I sent you. It basically says right here, at what rate is the volume changing? All right, so volume would be the variable, and we want to find its rate of change. So, we're on a roll here. That would be called dV dt, the change in volume with respect to time. Ouch. Why do I keep doing that? That hurts my finger every time I do it. Somebody here tell me to quit doing that, okay? Okay, but anyway, that, in my opinion, is what provides the motivation behind the third idea to differentiate with respect to time. Now, as mentioned earlier, this is two variables with multiplication between them, so we would need to apply the product rule to this, whereby we have this variable multiplied with that variable, and as you recall, each one gets a term being a derivative. So, I usually leave the first one alone. This is our product rule that we talked about weeks ago. So we say, all right, we leave that variable alone. That would just be plain old P. And then we differentiate this factor, again, with respect to time. All right, so much like we've been doing in the first few examples, in my opinion, this should be thought of as V in parentheses to the 1.4 power. In other words, the exterior operator is the power, and according to the chain rule, we would then do the power rule to that, 1.4 V to the 1.4 minus 1, that's 0.4. And then again, according to the chain rule, if we do the derivative of what's inside, so to speak, that would be expressed as dV dt, because remember, we're differentiating, so important, with respect to time. You're supposed to tell me to quit doing that. All right, well maybe you did and I just wasn't listening. I'm sorry. But anyway, the point is this would be the derivative of that second factor there. When do I get a turn to be a derivative? The P says to us. We say, your turn now. All right, so the derivative of P with respect to T, I'll remind you. Notice that time I didn't pound my hand there. I'm listening finally to you guys. But anyway, that would be dP dt. That's the derivative of that particular factor with respect to time. And then you've already been a derivative, V to the 1.4, so it just carries down as it is, right? Remember, you only differentiate one factor at a time while you leave the other alone, and each one gets a term, as we discussed when we did the product rule here. All right, now, you might think that's going to be dC dt, but it's important when you read this question that you take note of the fact that it mentions that C is to be considered a constant. So the derivative of any constant, as we know, is 0. Yay. All right. So there we are with that. And that's step 3, where we go through and we differentiate with respect to time. Now it's a matter of plugging numbers in and solving for the unknown. And again, I would mention to you that it makes sense to look at what you wanted to find, dv dt, and the point would be to go through here and treat that particular variable as if it's your what you're solving for, all right? So when we go back and read the question, we hopefully are going to find numbers to plug in for every other variable, and that'll remain a variable. So we go back, read the narrative, and here we go. When air expands abdominally, I don't know, adiabatically, I don't know, the scientists out there, I'm sure are like, you idiot, but that's okay. Anyway, it says at a certain instant, the volume is 400 cubic centimeters, all right? So that's just straight up volume. That's not how fast it's changing, it's the value for volume at that moment. And again, that was 400, so that would go in right there for the V. Might as well carry down that constant 1.4. And I'm probably over parenthesizing, but oh well. I would also point out there's another place where there's a V. So we'll put that 400 in that position as well, substitute that for that V. And of course the 0 is still over here. And I just kind of plug things in as I find them in the narrative, in the question. That's my overused word I'm noticing, narrative. Oh well. All right. It says at that instant, the pressure is 80. I think that's kilopascals. I'm not real familiar with that unit, but I believe that's what it is. That's how pressure is expressed. Once again, the scientists out there are screaming at me. Oh well, I'm sorry. But anyway, the pressure is 80. So that'll go in for P. All right. And then it goes on to say that the pressure is decreasing at a rate. Oh, that's the rate at which the pressure is changing. Important notice too, it says decreasing. But anyway, that 10 kilopascals, sorry scientists, per minute. There you go. Change in pressure with respect to time. 10. This is really important. It said it was decreasing. I don't know why. Again, leave it to the scientists. They know more than me. I'm just here to do the math. All right, but anyway, that pressure is decreasing. That's why that's a negative number. And then as mentioned earlier, the dv dt would be the variable. That's why it's so important to me to write down what it is that we wish to discover. What is it we're finding? This is just algebra now. Now we could leave this in symbolic form if we wanted to. In fact, I'm tempted to do that, and I believe I will. I understand I'm waving my hands and going, algebra now. But I think the 2 steps that would remain to isolate the dv dt would be, first of all, to add this over to the other side, correct? Because it's negative. So if you add that term over to the other side, that would give us 10 times 400 to the 1.4. I don't have a lot of space here. I apologize. But you can do it. It's just algebra. So you added that term over to the other side, and therefore it became positive in the process. This is gone now. And then since this is a multiplier in front of that, wouldn't the next step be after adding that over to divide this? So then this would be divided by the 80 and so forth. And look, I know we've had the conversation many times, and this is why we reviewed algebra at the beginning of the semester. This is calculus, and so when it's algebra, I have to just kind of buzz through those steps that are left. And we could do some canceling and some things of that nature, but I would ask you to please give your answers in decimal form, and therefore this is just calculator button pushing now, all right? And so I'm nervous now. I'm putting this in the calculator, and I hope it comes out right. The one thing that, again, I would always caution people is the safe thing to do is numerator in parentheses divided by denominator in parentheses. So, anyway, I know this is exciting watching a guy put numbers in a calculator and you can't see what I'm doing. And I would try to put it on the screen, but that just really is difficult at this time. I'm looking at my work. I'm really nervous because, again, this will be on video that everybody is going to scream at me if it's wrong. And I believe I'm good. I think this comes out to be approximately 35.7143. Again, however many decimals, I don't care. I'm gonna put that in again, just to be sure. You know, I could have done some canceling with the 400s and things of that nature. Oh, well. You guys are off having a sandwich now or whatever. Yeah, I got that same number again. So volume again, volume would be expressed as cubic something or others. What do we have here? Cubic centimeters. So volume, cubic centimeters, I'm just gonna put centimeters cubed. And then time is expressed throughout the entire question. I'm getting lost, I'm sorry I'm too close here. Where is he, you dummy? There it is, minutes. All right, cubic centimeters per minute. So there we go. As always, I hope that made sense. And so that's how fast that volume was changing at that instant. That was exciting, wasn't it? I am really looking forward to looking at example number 5 with you here pretty soon. So we'll see you again. Take care. Go get a cup of coffee or a sandwich or something.